presentation, Arnaud is then going to show you a demo on ST hardware, and then Tanmay is going to show you a demo on AMD Xilinx emulated hardware. Next up, Dan is going to talk about other VirtIO devices in an AMP system. So this is hypervisorless VirtIO. Thomas and Bruce are then going to show how you can use system Devicetree to configure all these different OSs from one single place. In the wrap-up, we're going to show you, talk about what's next for each of these technologies, how you can try this on your own, and then we'll have some live Q&A. So the OpenAMP project is a lightweight open source project with open governance. It's a Linaro community project. You do not need to be a Linaro member to be a member of a Linaro community project, and the same is true of OpenAMP. This is our membership today. So OpenAMP works on a number of different areas of IPC and resource sharing, but we'll talk about that in the next slide. So this is the mission. This is the typical layout of a AMP type system that OpenAMP would be addressing. So you have a couple of cores over here on the left running Linux, and that's in an SMP type system, in an SMP way. And then core B0 here is running an RTOS. Now core B could be completely different than A. And then core B1 is running bare metal. Also could be completely different than the others and not capable of SMP. So this is the kind of differences in OS and cores that we're talking about. You can see here that the memory is shared between the different systems. So some of it is parceled up. So some of it is privately used by a given OS, and some of it is shared by two or more of the OSs. Each of the peripherals is assigned to one of the different OSs. So this requires a lot of coordination and communication, and that's really what OpenAMP is about. So in OpenAMP, we work on technologies. So technologies are independent of implementations. So remote proc and rpmsg are the first things that OpenAMP worked on. We'll talk about the history in just a second. And now we're adding other VirtIO devices into the mix, and that's what Dan is going to talk about. System Devicetree is that evolution of Devicetree where you can use it to configure all the different OSs. And then if there's anything else that fits into that OpenAMP mission, it's open to be a topic in OpenAMP. So if you have ideas and want to work with us on that, that would be great. Come join us and tell us about your ideas. So then we also work on, besides just the technology, we work on the implementations. We do a lot of work in the Linux kernel, and we'll talk about that today. And then OpenAMP itself has the OpenAMP library and libmetal library, which work on MCUs and SoCs. They work on RTOSs. They work bare metal. They can even run in Linux user space. We have our own Yocto OE layer, Meta OpenAMP, which helps you build this stuff if you're using OE. And then for System Devicetree, the implementation is Lopper, which is a tool created in the past couple of years, and it helps you do this. And Bruce is going to show you a demo of that, and Thomas is going to talk about what it's doing. All right, so a little bit of a history lesson on OpenAMP. So remote proc and rpmsg entered the Linux kernel in version 3.4, which is 2012, so we're going on a decade. The OpenAMP and libmetal libraries go back to 2013 and 2014, and the OpenAMP project itself was first founded in 2015 and with a press release in 2016. In 2018, ST, Xilinx, and Linaro worked to get OpenAMP adopted as the standard IPC mechanism in Zephyr. And in that process, we found that the libraries were a little heavy, so there was a good bit of work to do to skinny those down and make some portions optional if you didn't need them. So that work happened, and then that was successful, and OpenAMP is an important part of Zephyr. 2019 and 2020, the project relaunched as a Linaro community project. This is what I talked about earlier. And this makes the organization and the governance a little bit more formal. Also at that time, Linaro added another kernel maintainer that works in these areas, and Matthew is going to be with us in the Q&A session. So then finally in this year, at the beginning of this year, I talked about how OpenAMP project is lightweight. There's no people resources in OpenAMP. So all the engineering being done is volunteer from whoever, the member companies, whatever they want to work on. In Linaro, we're a cooperative organization, so HPP is a way for the member companies to decide what we want to work on in OpenAMP. And our sponsors today are ST and AMD Xilinx. All right, so now we're going to talk about Upstream, Remote Proc, and rpmsg. So what are Remote Proc and rpmsg? Remote Proc is a facility to let you load, start, and stop firmware on remote processors. It lets you do crash detection, crash dump, crash recovery. It can optionally, normally, but optionally, parse a firmware resident resource table that describes to the person loading it, normally the kernel, what resources that firmware needs, and this is how the person loading it, the remote proc host, the kernel normally, knows what resources the remote proc needs, and this is how they coordinate on it. A fairly new facility for Upstream is the capability to have the remote processor already running when the Linux kernel starts. In this way, so the Linux figures this out and starts up remote rpmsg to the remote processor, but doesn't necessarily control the remote processor. This is important if you needed to start that remote processor early for a boot latency requirement, or the remote processor is a safety function and the kernel needs to be hands-off. So this capability is important for those kinds of situations. This is not a new facility. This facility has existed before in vendor SDKs, but this is really, getting this upstream was it happened in the past 3 years. So it is relatively new from an upstream point of view. Qualcomm has added a facility to have the remote processor become a device node in the dev file system. And you can control the remote device from there. In our demos, we're going to show peeking and poking at it from sysfs. So this is an alternative to the sysfs peeks and pokes. It allows them more control in their specific requirements. Qualcomm's the only one using this today, but it's an interesting idea, and maybe we'll look at it more. So rpmsg, fundamentally rpmsg is just an IPC mechanism. It's a multiplexing layer, just like TCP or UDP is. So it has multiple port numbers. And then it has name-based port resolution. So you can do a name announcement, and that name announcement will associate a port number with a name, so you can do late binding to the port numbers. There are multiple providers of rpmsg in the kernel. In OpenAMP, we focus on the Virtio based rpmsg. Qualcomm also has G-Link rpmsg, and they use this to talk to their dedicated firmware like modems and sound processors and things like that. So rpmsg can be used in kernel through a kernel API. or through dev nodes that get exported to the DevFS. And relatively new facility, at least for the Virtio rpmsg, is having a Linux user space export a named endpoint. Another new facility is the remote processor being able to do a name announcement that then causes Linux to create a TTY device, and you can interact with that TTY device as you would any other TTY device, and that TTY device is implemented over on the remote processor and could actually be talking to a real UART, but maybe more commonly is just talking to the software on the remote processor. So Arno is going to show you both of those new facilities. These are the people that are using rpmsg in the kernel today. I suspect that there are more in vendor kernels. So if you're one of those people, maybe now's the time to get your use case upstream. So why is upstream important? So these technologies have been existing for years. They've been in the vendor SDKs. But maybe the vendor SDK was using the vendor kernel to do that, and there were missing pieces to make that work upstream. Or there were the vendor was using proprietary tool that you needed, or maybe all the pieces were upstream, but nobody was showing you how to assemble all those pieces. So we thought it was important to start with the upstream and show demos and use cases just using upstream. So, and that's why we created the OpenAMP CI builds. So the CI builds, the idea is that we can build with any kernel we want, the very latest kernels, old kernels, RC kernels. In the future, we want to be able to use this to test patch series as they come to the remote proc mailing list. But for now, we're using it to build, and we're using Yocto OE to build. So we have a very minimalist system with Pocky and Meta OpenAMP. We do bring in Meta ARM, and this is to get the generic ARM64 machine definition. We also have our own layer that's really just for CI purposes. We don't intend other people to use this in the Meta OpenAMP BSP layer. And that provides a generic ARM v7 machine definition. The idea is that we be able to build one ARM64 OS image and one ARM32 OS image, and then those images should work on multiple platforms. The platform, the board, provides the firmware. This is as defined by System Ready. So he provides the boot firmware, and then the OS boots it. The OS boots via that. So that's how we're defining things. We have one ARM32 platform and one ARM64 platform that we're testing today. We hope to add others to keep us honest on this multi-platform capability. So why Zephyr? The libraries are portable. They work on multiple RTOSes. They work on bare metal. They work on Linux user space. But we have to start somewhere on the CI, and Zephyr, we believe Zephyr was a good place to start. Zephyr is non-trivial. It has lots of bells and whistles we can use in demos and things. We can show minimalistic systems. And I think most importantly, it has the same developer flow, regardless of which vendor SoC you're starting with. So you can start with one and then apply the knowledge to the others. Once we've automated one, we've automated it for many. So that's, and the build tools are all provided by Zephyr as well. So it's a good place to start, and that's where we're starting. The OpenAMP build. So we provided an OpenAMP system reference repository where we have demos and a Zephyr manifest. so we can start building these Zephyr images. By manipulating the manifest, we can test with Upstream Zephyr or an experimental branch like the Virtio branch, or we could just test the latest version of OpenAMP and libmetal before it's been adopted by Upstream Zephyr. In the future, we want to be able to build PRs to the libraries as they come in for regression testing and that sort of thing. And we also want to automate the release testing that happens twice a year for these libraries. So do as much as that in an automated fashion as possible. So I said lots of interesting stuff has happened in the past 3 years. So I collected these statistics. If you look at remote proc in the kernel, you can see that more patches have come in the past 3 years than in the previous 7 years. But if you look at rpmsg, you can see even there the rate is per year, the number of patches has accelerated. In the OpenAMP library and libmetal, again, very active in the past 3 years. We're getting more collaborators than we have in the past. So always interesting to get new people, new perspectives into the project. So I thought this was very interesting. And then from an adoption point of view, if you look at, I don't know about you guys, but I'm pretty stingy with my stars on GitHub. So the number of stars that the OpenAMP library has gotten over the years is on this graph, and you can see that the adoption looks pretty good. So once again, the OS, the libraries are portable to multiple OS and OS situations and multiple architectures. So this technology is ready for you as a user or you as a platform provider. So start using it or start putting your application, your community, your platform in here as well. So next, we'll have Arno demonstrate Linux and Zephyr on the ST platform.
Hello, my name is Arno Pouliquin. I'm software engineer at ST Microelectronics. I'm also one of the maintainers of the OpenAMP libraries. Today, I propose to show you some demos around evolutions of the rpmsg and remote proc frameworks. For this, I will use a ST Microelectronics board named the STM32MP157F Discovery Board. On this board, we have STM32MP157F SOX, which embeds a Cortex A7 dual-core and a Cortex M4. The Cortex M7 will run a ST-OSS Yocto distribution based on the Upstream repository, the Linux kernel 6.0, the ARM trusted firmware, the U-boot, and the Opti. The Cortex M4 will run the Zephyr 3.2, which integrates the OpenAMP libraries and an OpenAMP system reference example, which is available on the GitHub of the OpenAMP GitHub. For my first demo, I will show you how to load a Zephyr firmware and start it on the coprocessor using the remote proc U-boot framework. Then we will start the Linux and attach the Linux to the Zephyr framework for interprocessing communication. This kind of setup is useful for customers who want to perform some action before the Linux is started. For the second demo, we will focus on the rpmsg protocol. On Linux side, we have now 4 generic rpmsg devices. The first one is the rpmsg char, which has been introduced by Qualcomm and is now also available for the Virtio transport layer. The second one is the rpmsg control, which allow to expose to application some endpoint, but also now it's able to start and release some rpmsg services on associated rpmsg devices. The rpmsg TTY, which implements the serial protocol over rpmsg, and the rpmsg client sample, which is a legacy sample that allow to play with the rpmsg protocol. On Cortex-M4, we will run Zephyr with 3 threads. Each thread will answer to the one Linux rpmsg driver. The rpmsg TTY services will respond to the rpmsg TTY Linux driver. The rpmsg raw services will respond to the rpmsg char Linux driver. And the rpmsg client services will respond to the rpmsg client sample. All these services use the rpmsg protocol integrated in the OpenAMP library. Now let's move on the demo. For the demo, I will use documentation already available on the OpenAMP GitHub. The first one explains how to build and load firmware for the STM32MP1 board. And the second one explains how to play with the rpmsg devices. So first, let's try to load and start the firmware using Ubuntu Remote Proc framework. Here we have the board console. So first of all, we have to reboot the board and switch on the U-boot console. Okay. So now the first step is to get the firmware from the file system. So we get the rpmsg multiservice.elf from the bootfs partition in the SD card. The firmware is loaded in an image in DDR. Then we start the Remote Proc framework. We load the firmware in the Cortex-M4 memories. We start it. And then we continue the boot sequence. So now the Linux kernel is starting. Okay, we are now in the Linux console, so we can check the state of the coprocessor. We can see that we are in detached state. That means that the Linux detects that the coprocessor is started, but is not yet available to communicate with him. To be able to communicate, we have to start the Remote Proc framework on Linux side. And then we can see a lot of message on the console indicating that the Linux attached to the coprocessor. We have the message of the attachment, and we can see that we have here some services that have been started. The rpmsg client sample services, the rpmsg TTY, and the rpmsg raw or rpmsg char. And then we can see a lot of messages which are communication of the rpmsg client sample driver with the remote side. He sends some message and wait answer from the remote processor. If we check again the state, we are now in attached state. So we can now play with the rpmsg devices. So let's first check the different devices which has been probed. We have the rpmsg 0, which corresponds to the rpmsg char services or raw services, the rpmsg control, and we have also the rpmsg TTY devices. So we can try to communicate with the remote processor thanks to the rpmsg TTY 0. So first I run a cat in background to UL to read the device, and I send a message to the remote side. The Zephyr answered to me, replying with the same message, and adding a prefix TTY0 means that he uses the TTY0 endpoint. Now if we want to create a new rpmsg TTY device or TTY service, we can use the rpmsg control, and especially the rpmsg create dev IO control and the rpmsg release dev IO control to release this device. To observe what's happened, I propose to add some dynamic traces to dump message exchange between the Linux and the remote processor. So to create a new instance of the rpmsg TTY driver device, I use an application which is available on the OpenAMP GitHub in the rpmsg util package. This application will create the new device thanks to the rpmsg control 0. So the service created is the rpmsg TTY and with the local address 257. If we have a look to the kernel message, we can see that we send a message to the remote side. We send what we name the enhanced announcement, is the name service announcement, to expose the local service to the remote side. So here it's the rpmsg TTY, and we can see here that we create a local device. Then the remote processor create its own endpoint to communicate with this Linux rpmsg device, and send here a dummy message to provide his own address to the Linux. So for this communication, the Linux address is 101, that corresponds to the address 257, and the remote address is 400. We can now communicate also with the TTY rpmsg 1. We can first check that the device exists. I run a cat in background to read the device, and then I send a message to the remote side. So here we can see that the Zephyr answer with the first message bound that is still in the TTY buffers, and the new one, which is the hello device 1, we sent with the prefix TTY1. If we have a look to the message, we can see that we send here a message to the remote side, hello dev1, on the remote side, answer to us TT1, hello dev1. Now, if we don't need any more of the rpmsg TTY1, we can delete it. For this, I use the same command, but with the -d to ask to delete this service. We can see that the cat which was running in background is now closed. And if we have a look to the list of the TTY RP message, we can see that the TTY RP message 1 has been released. That's all for my demos. Thank you for your attention.
Hello all, my name is Tanmay Shah. I am embedded software engineer at AMD Xilinx. Today I'm going to introduce Xilinx Sync platform, Sync MP platform briefly and execute the few demos that shows OpenAMP in action on Xilinx Sync MP platform. So Xilinx Sync MP platform has 4 ARM Cortex A53, which is referred as APU, that is Application Processor Unit, and 2 cores of ARM Cortex R5, which is referred as RPU, that is Real-Time Processing Unit. Apart from these, there are many other hardware blocks, such as micro-based controller, GPU, programmable logic, FPGA block, and so on. Its technical reference manual is UG1085, which you can refer from a link given in the presentation. So for various operations between Cortex A53 and Cortex R5, OpenAMP is used. Also, we use remote proc implementation in Linux kernel and rpmsg implementation in Linux kernel. So Cortex R5 can be configured in 2 modes. One is lockstep mode and one is split mode. We will see operation of each mode in detail. So in lockstep mode, both cores uses same set of resources that such as interprocessor interrupt, TCM, that is tightly coupled memory, and so on. So they both execute same instruction, and so the same firmware ELF is loaded for both the RPU cores. And our main core is core 0, and core 1 checks matches its output with core 0's output. And if there is a discrepancy between 2 outputs after executing instruction, system error is raised. And so that is why this is also known as safe mode, because if there is any discrepancy in instruction execution, we get to know immediately. So the second one is split mode. In the split mode, each core operates independently, and so each core has its own set of resources. So each core has its own IPI to communicate with APU, and also IPI for communicate between 2 R5 cores. Also, each core has its own set of TCM and reserve memory region, where we can load a separate ELF file or separate firmware for each of the core. And each core executes separate firmware instructions from separate firmwares. Now we will see OpenAMP in action on Xilinx Sync MP ZCU102 board, which is emulated by a QEMU emulator. So all the binaries needed for this demo are available in the Docker image. I will run Docker with this command. As you can see, there are multiple demos, and each demo has a soft link. We will run a first demo, which configures R5 in lockstep mode, and will execute multiple examples that shows OpenAMP functionality on Xilinx Sync MP platform. So this is a tmux based setup in which first window is schemo. It is loading necessary binaries such as image, kernel image, rootfs, system device tree via TFTP, and it will boot the kernel and rootfs. Second window is Docker. If you want to exit and terminate this schemo session, we just write exit here. Second and third window, third and fourth window, they are UART for RPU, but for our demo purpose, we will use the same UART as of APU. So Cortex-R and Cortex-A, they both are printing on the same UART. So now we will log in on this console with root username. We don't need any password. So the first demo that, so the first example I'm going to run is demonstrate simple rpmsg communication between Cortex-A, which is host processor, and Cortex-R, which is the remote processor. For our demo purpose, Cortex-A is always host processor and Cortex-R is always remote processor. So first of all, to know whether remote proc framework was successfully loaded and our platform driver was successfully loaded or not, we can check sysfs, if sysfs nodes are created properly or not. You can see there is one directory under remote proc. This represents Cortex-R5 in lockstep mode. And there are multiple nodes under it. So firmware node we will use to assign a binary name to binary or elf file name for Cortex-R to boot, which is available usually under lib firmware. So for matrix multiplication demo, we will use matrix multiply binary. Here we have assigned the binary. We can check that yet remote processor is in offline state, which means it's not loaded anything. We have just assigned the binary name. Now, when we start the remote processor with start command, at this point, after this executing this command, a remote processor will boot the firmware. We can see it has created one rpmsg channel for communication with host processor. At this point, we can check state of remote processor. See, it is running. Now, this utility we will execute on the host processor, which will generate two random matrices, and it will send both the matrices using rpmsg protocol and rpmsg implementation in the Linux kernel. It will send both the matrices to remote processor. Remote processor will receive the matrices, it will multiply it and send the result back to host processor, and host processor will print the result on the same console. So as you can see here, the two matrices were generated, and host is printing the result of the multiplication. Now we will stop the demo. So here we are stopping the remote processor with this command. And we can check the status as well. So at this point, remote processor is offline and it's not executing any more instruction. So the next demo that we are going to execute demonstrate how remote processor can use host processor's file system and how remote processor standard I/O can be redirected to host processor's standard I/O. This is achieved with rpms with a proxy service implemented in OpenAMP. So first, we will load necessary ELF file that is available under lib firmware directory. Then we will start the RPU, which is remote processor. It will create a it will initialize remote proc, initialize rpmsg, and create any required resources for rpmsg, such as shared buffer pool, and eventually it is creating OpenAMP rpmsg demo channel. As you can see here, initializing IO redirection. So on the firmware, we'll initialize IO redirection using implementation using proxy implementation in OpenAMP. So at this point, we will execute proxy app on host side, which will communicate with firmware on remote side, and then it will allow a remote firmware to make use of host processor's application, host processor's file system. So as you can see, first remote processor has started file IO demo, which is nothing but using host processor's file system. So here remote has opened a file with name remote.file on the host processor. Then it is writing, this is a test string being written to file. This string in the file, and then it is closing the file. So when we exit from the demo, we will see the we will see a file name with a remote.file created, and with which contains the string, this test string. The second demo, which is IO redirection, is interactive, and so here, this remote processor firmware on the remote side is waiting for user input, and it is basically using a scanf function to scan the string which is entered from the host side. So we will enter some string here. Then enter age, which means we can enter any integer. And then enter value for pi, which means we can enter any floating point value. So what we just did was we entered everything on the host side, and because remote side IO are redirected to host side, remote can also scan whatever we enter on the host side, and remote will use printf function to print something on the host console. And this is very helpful in case of bare metal firmware where there is no file system implementation available, but we still want to make use of host processors, host side file system. So that can be achieved with OpenAMP software stack. So that can be achieved with OpenAMP software stack. So as you can see, this remote.file contains the test string that was written by remote processor.
Hello, my name is Dan Mile and I work in the Windover office of the CTO on emerging technologies. Today I'll be talking about hypervisorless Virtio and how it can be used to assemble connected heterogeneous multi-OS systems. Modern SoCs are powerful multiprocessing compute platforms aggregating multiple silicon building blocks like application processors, real-time processors, programmable logic, sensors, and various types of accelerators like FPGAs, GPUs, DSPs, TPUs, and others. Many functional components come together in a software-defined architecture which combines mixed criticality services on shared or centralized compute, safety-certified operating systems and bare metal applications for safety-critical functions, real-time OSs for early functions, and rich operating systems like Android and Linux for tasks like dashboard, IVI, or navigation. Software now fundamentally defines a product and the functionality it provides. Applications take the form of workloads which are either virtualized or deployed to dedicated partitions, and more often than not, appear in both forms in complex intelligent edge deployments. We call these hardware partitioned or software partitioned execution environments safety or real-time islands, depending on their purpose. I'll refer to these partitions as compute islands. Partitioning applications and services with their own OSs decouples subsystem development, limits interdependence and interference, and improves lifecycle management. This also reduces testing, since only changed subsystems need to be unit tested, while the rest of the system can be validated with system-level integration tests and via stability monitoring. It's important to mention that the runtimes in these partitioned systems do not exist in their own bubbles. The nature of embedded systems requires communication and interaction among the various subsystems, so any consolidated hardware-software solution needs to take into account the communication interfaces used by the individual elements. Secure and reliable communication channels are of paramount importance. This in turn requires more software for communication, middleware, high-level services, and frameworks. What about the devices these embedded applications need to use? When possible, devices can be directly assigned to compute islands, either in a dedicated CPU cluster, pretty much machines on their own, or passed through to a virtualized application. Usually, the overall architecture tends to be a bit more complicated, so some kind of resource sharing is needed. To an extent, hypervisors can provide a solution for this type of problem. Let's switch gears for a moment and talk about Virtio. The Virtio transport abstraction was originally developed at IBM for virtualization of Linux-based guests. It now serves as a standardized interface that hypervisors provide for virtual hardware presented to guest operating systems. In a standard hypervisor deployment, Virtio can enable guests to achieve high performance by eliminating some of the complexity and latency associated with interruptions in guest execution. Virtio has specifications for devices which support a lot of the advanced features we expect from any modern runtime: console, networking, virtual sockets for IPC, file system services through 9P or VirtFS. Virtio is a good solution for intra-SoC communication because it is an open standard, it decouples software from hardware, it solves the fragmentation problems caused by hypervisor-specific interfaces and device driver implementations, it supports multiple transports, it increases efficiency, and it is already supported by many operating systems. The memory-mapped I/O Virtio transport is interesting because it can be used both to communicate downwards to an embedded hypervisor, but also to communicate laterally between runtimes deployed on a multi-core CPU SoC. This lateral Virtio has been labeled hypervisorless Virtio. The goal of the hypervisorless Virtio initiative is to define and prototype a framework for using Virtio as a communication infrastructure on heterogeneous multiprocessing platforms. Hypervisorless Virtio runs on ARM and Intel, uses MMIO over shared memory. It uses hardware notifications instead of hypervisor-based notification mechanisms. And it includes a custom Virtio backend derived from the Linux KVM tool, which we call a physical machine monitor. Hypervisor Virtio supports Virtio console, 9P virtual file system, virtual sockets, Virtio net, and entropy devices. This is a general overview of the Hypervisor Virtio architecture. Some devices can be assigned exclusively to one of the runtimes, but Virtio provides the infrastructure for communication and resource sharing between runtimes. In both runtimes, applications use standard APIs to communicate. Here we can see how hypervisor Virtio differs from standard Virtio. In classical Virtio, data can reside anywhere in guest memory space because the hypervisor can't access it. In hypervisorless Virtio, though, the data needs to be in a pre-shared memory region, and there are various mechanisms to ensure this. We can either change the drivers to allocate data from the shared memory region, or we can keep the drivers unmodified and use bounce buffers to copy the data to and from the shared memory region. As a library, OpenAMP provides the software components which enable the development of software applications for AMP systems. And it already includes support for Virtios, the structures which provide the data transport abstraction for Virtio, since they are successfully used in the OpenAMP remote processor messaging framework. These reasons provide enough justification to involve the OpenAMP Application Services Working Group in the hypervisorless Virtio activities. Where are we with Virtio and hypervisorless Virtio supporting the OpenAMP library? We have the building blocks for creating OpenAMP-based Virtio frontends, which support network, console, and entropy devices. The hypervisorless Virtio mode of operation is available for the network and entropy devices. Zephyr is our runtime of choice for demonstrating Virtio, and we have samples demonstrating standard Virtio with QEMU ARM as virtual machine monitor on a QEMU Cortex A53 target. QEMU Cortex R5 is the target for hypervisorless Virtio in a configuration based on the Xilinx ZCU102 platform. In this case, the Virtio backends are implemented in a fork of the KVM tool VMM, which is available in the OpenAMP system reference repository on GitHub. The demo I'll be presenting next shows a hypervisorless Virtio deployment with Beta Linux as the main runtime on the A53 cores and Zephyr as the auxiliary runtime on one of the Cortex R5 CPUs. A section of shared memory is reserved for hypervisorless operation, and the Xilinx interprocessor interrupt mailbox controller provides notifications. The physical machine monitor runs as a user space process on Beta Linux and includes a pseudo-state machine for handling Virtio requests. If needed, the PMM can act as a proxy and upload some processing to vhost modules like vhost net or vhost vsoc. Binary-only version of the hypervisorless Virtio setup can be used in a containerized deployment based on the OpenAMP demo light image from Docker Hub. In this container, I can start a QEMU-based ZCU102 virtual target. This is a Tmux-based split pane environment, which includes the Beta Linux console, 2 additional console panes for the ZCU102 UARTs, and a demo container host shell pane. I log in and run the hypervisorless Virtio demo setup script. The physical machine monitor has started, and the setup script has created a tap interface and assigned an IP address to it. In the host shell pane, I'll SSH into the QEMU machine and start the Zephyr instance on the first Cortex R5 CPU. The Zephyr command shell is available in the second UART pane. I can see that the entropy test, which runs when the Zephyr kernel starts, was successful. I can now interact with the Zephyr system using shell commands. If I display the device list, I can see the RPU0 IPI device, which provides notification support between the two runtimes. The Virtio devices which are available in the system are also present: an entropy device and the Virtio network device. I can show the IP address of the Virtio network interface and then check connectivity between the two runtimes. I'll switch to my Zephyr development environment to show you a sample of the regular Virtio support provided by libopenamp. The sample I'm running is a basic DHCP client sample for QEMU Cortex A53, which when run starts the Zephyr kernel in a QEMU instance. The network interface is a Virtio net device. I can see that the DHCP client has successfully assigned an IP address to my virtual machine. And I can ping the host on its IP address. I hope this presentation has piqued your interest. If you want to learn more, please get in touch with the OpenAMP project.
Hi, my name is Thomas Emerson. Today I'm going to talk about system device trees, and in particular, Bruce Ashfield is going to do a couple of Lopper demos. We're going to look at some simple device trees that just shares some memory for Virtio between a couple of OpenAMP domains. And we're going to look at a more complex example using Zen. So before we get into the demos, let's remind ourselves, what do we mean when we talk about device trees? Well, device trees have been used for a long time for Linux and other operating systems. And what it does is that it describes all the memory, the CPUs, and your peripherals for that operating system. Typically, it's just been one address space. What's viewable from Linux as an example. What we've done with system device tree is that we have added a couple of things here. One is to describe all of the resources in the system. So if you have other CPU clusters, if you have multiple memory buses that perhaps are not visible for your Linux partition, well, you can describe that as well. The other thing we've been adding is a way to allocate resources. So you can tell your systems how much memory is going to Linux, how much memory is going to an RTOS as an example, which peripherals goes where, which CPUs are running what. So that's the allocation of it. And the idea is to have one true source that describes all of your system and how it's allocated for your system software. Lopper is a framework. It's an open source framework that can manipulate device trees, both regular device trees and system device trees. The typical use case of Lopper is that you take a full system device tree and then you cut out away the branches that doesn't apply to you. So when you create a Linux device tree, as an example, you take away everything that only goes to the RTOS, so you don't see that. And that way you can create a traditional device tree for Linux that it knows how to handle. But Lopper can do a lot of other things. It can also filter out things. Maybe your device tree for your RTOS looks a little bit different. Maybe you have some different naming conventions and things like that. So think of Lopper and something we call LOPS, which is something you write in device trees, a data-driven way of manipulating stuff. Think of it as a set script where you can recognize some part of the tree and then you can do some actions on those. If you have some more complex things that you need to do, then you can write an assist, which is a Python code that then plugs into Lopper, and you can do really advanced things if you want to. All right, the first demo that we're going to do is an OpenAMP demo. OpenAMP has lots of aspects to it, and as you have seen in this webinar. But here in particular, when you're doing some messaging over Virtio, when you want to set up those Virtio shared pages, how do you do that in one place? As we're going to demonstrate that. And again, you're going to have a system device tree, a specification. So think about the specification as this basket of all the available resources, CPUs, memory, peripherals. To that, Bruce is going to show a YAML file, which is the allocation of these hardware resources. In this first example, we are going to have two different domains, one for Linux and one for a bare metal. The Linux is running on the Cortex-A's on 4 A53s, and we're going to allocate some memory and some devices to it, and also have some shared memory. And then the other cluster is running on the R5 cores. And we're going to demonstrate how we use Lopper to then prune this device tree and create the regular traditional device tree for Linux. And we're going to make some changes in the YAML file and see that with one source, we then can very easily change what you generate and how Linux and the bare metal will look at the system. This demo is in a self-contained Docker image, so you can try it out yourself. At the end of the webinar, you'll see how you can download it and use it. The Lopper commands that we're showing, Bruce will be showing, they can look a little bit complex, and Bruce will go through on why we're including different types of assists and lops, and how that then can configure the system for you. And the key takeaway here is that you change one YAML file, and that flows through your whole system through all your different domains. All right, here's the first demo.
Hi, my name is Bruce Ashfield, and I will be demonstrating some of the Lopper commands and workflows that can be done in the Lopper framework, as was just previously described by Thomas. We'll be looking at how a system device tree can be fed through a set of OpenAMP assists and LOP files to produce a bootable Linux device tree, as well as some other configuration values that would be used for a bare metal or other build system synchronization. I'll then also be demonstrating how the same Lopper command with different inputs and assists can be used to extract a device tree snippet, if you will, and pass to a Zen guest so that we can coordinate a Zen DOM0 and a Zen host, which is actually very similar to the OpenAMP case. We'll be showing both a lot of the components that were talked about before in the Lopper framework. So there will be input YAML specifications. There will be assists, which are Python implementations of tree logic, as well as some LOP files, which are simpler commands that are read and executed by Lopper against a tree. The first run that I'm going to do will be, it is an an extracted Lopper call that's normally part of a OpenAMP build within the Octo project. This is run as part of the build in order to produce a bootable Linux device tree, which is then integrated into an image and booted. And it makes sure that the Linux boot device tree, as well as the configuration for the different sides of the AMP system, are all in sync. So if we look at it here, there is a few things going on. There's a big command line, which is normally, like I said, wrapped or part of a build system. But we are running Lopper directly. We are loading 3 different assists, which is the OpenAMP the OpenAMP Xilinx, and the OpenAMP Xilinx Zinc. So that is just how we decided to split the logic in this implementation. So there's this generic OpenAMP assist. It's doing domain processing, subsystem processing, and some device manipulation that are generic to, say, any OpenAMP configuration you might have. We're then doing some Xilinx specific tweaking in the OpenAMP Xilinx assist, and then finally we're doing some board specific things in the Xilinx Zinc assist. It is also taking an input, which is a YAML file, and this is the specification of domains, devices, and other configuration settings that are described by the system device tree specification. We then have a series of lot files which are either doing smaller tree manipulations or they are coordinating the overall flow of commands. So we have one that's doing a translation from YAML to add more information. We have one that's looking at the A53 interrupt muxing, one that's looking at the domain for Linux, one that is tweaking it for the board, and finally one that is pruning away things that we don't need in the final output device tree. That pruning step is important because there's parts of the system device tree that Linux either doesn't care about or doesn't use or doesn't understand yet. So we remove those to make sure that an existing operating system does not have to be tweaked to work with the output of Lopper and a system device tree. If we now have a look at the YAML file, which is the specification input in this case, these can actually also be a DTS input, but typically it's a lot more user-friendly and easier for somebody who wants to configure the system to manipulate this YAML file versus knowing device tree syntax. So if we look at it, we see we have some definitions that will be referenced later in the file, followed by some domain specifications. In our case, we're only looking at the A53 cluster because this is going to be what Linux is using. It has some compatibility strings, and it sets the CPU and mask, has access to a couple of devices, sets up some reserve memory, and then does a domain configuration. And you can see in the reserve memory, it is referencing those definitions from above. So we're setting up these different VRings and rproc settings. These are what will be applied to the input system device tree in order to produce the bootable Linux output tree. So I ran that command previously when I pasted it in there, and you can see it took a system device tree as an input and produced something called Linux boot.dts. So if we have a quick look at Linux boot.dts, we can see that, yes, in fact, it is a standard device tree. And one thing that was added in particular that was mentioned in the YAML file is this reserved memory node was created, and the values for rproc 0, rpu, vdev ring 0, etc. were pulled from the settings in that YAML file. So we've now made sure that the booting device tree matches the input specification. I've also prepared a second device, a second YAML input that, if we have a look at it, it changes some of the values to show what sort of manipulations you might want to do when configuring the input. In this case, we are changing the address and the size of one of the VRings. We are changing the overall memory allocated to Linux, and we are allocating a new device to the domain. So if I do a diff between those two commands, and we have a quick look, you can see that, so RPU, VDEV, VRing 0, I've changed the start address to be 00 coffee, because everybody needs more coffee, and I've changed the size. Those are not really valid values, they're just set so we can pick them out more easily in the output. I've also added to the access specification 2 Ethernet devices that we want to be made available to the A53 domain. And finally, I am changing the memory overall for Linux to have some Sentinel values that we'll be able to pick out more easily. So when we run the lopper command again, we will use the new that new YAML file, but otherwise everything else is the same. And we will actually ask this to output to something called Linux boot 2 DTS so we can have a quick look at the differences between the two. So when we run this command, it's now applying the different types of settings, manipulating the device tree and changing the corresponding output. So if we take a look at the difference between Linux boot.dts and Linux boot 2.dts, there's not a lot of changes, but they're important. So if we scroll up a little bit, we can see one of the things in particular that was added is we now have a Ethernet device that has had any of its dependencies and p handles adjusted appropriately, and it's been pulled into the domain that the DTS file that Linux will see as it boots. We can see that secondarily that this PSU DDR0 memory has had its addresses changed in the reg field to match those Sentinel values that I put in the configuration. So we've now changed the overall memory, the DDR memory specification that Linux will see. Some of the other differences in the file are some adjusting of p handles because we added the Ethernet. It needed a p handle, therefore there was sort of a chain effect throughout the file, adjusting of that. And then the final change that I mentioned was I tweaked the addresses with for the VDEV0 vring, and you can see now that we have the new base address and size that were specified in the YAML. So just by tweaking that YAML input file, all of those different elements have been coordinated and will be passed to Linux to boot. But in order for our system to work, there's often a bare metal driver or something running on the other part of the system. So we need to make sure its values are coordinated with the Linux values. And that was normally, it could be done by hand. Of course, it's error prone. So there's a secondary output from the assist as they run this, and we get something called OpenAMP channel info.txt. That is simply a produced file of values that match. You can say you see the vring base is that coffee value that I set. The size is the new one. These are the values that will be pulled into a bare metal or an application build to make sure that they're coordinated between the two. Nothing is error prone. All one change to one YAML file, and all of the different operations have been coordinated and executed. And that is what we wanted to show for Lopper, System Device Tree, and OpenAMP, and how the coordination between the domains and the different outputs works.
Next demo is a little bit more advanced. We're going to look at the device trees for Zen, the embedded hypervisor. Before we get into what we're going to demonstrate, just want to show how system device trees can be used for some much more sophisticated examples. In this case here, we have the same system device tree specification as before, but the allocation is much more advanced. Here we have hierarchical domains. The outermost domains, called subsystem 1 and subsystem 2, they actually denote all the hardware that belongs together from a life cycle point of view, meaning when you boot up things. So imagine a system where you have some critical software that needs to run all the time, but then you have some other software that, every now and then maybe does crash, so you have to reboot it. It hasn't been safety certified and so on. But you want to make sure that you know exactly what hardware you need to bring up from reset again and which one you should leave alone. So the firmware needs to know all that information. So this is something we have implemented on the AMD Xilinx SoCs as a way to handle these more advanced lifecycle scenarios. Within the subsystem, in subsystem 1, we have one domain. It's a Zen, it's a hypervisor domain with 2 guests, Linux 1 and bare metal 1. We have some cores into that, so 3 cores for Linux, 1 for the bare metal. We have some devices into it, and then some memory, and some memory is shared. And then we have another subsystem with the FreeRTOS on a couple of R5 cores, and we have a bare metal partition on the microblaze. So again, this is just showing how sophisticated it can become when you have these modern SoCs that has lots of different execution areas. What we're going to show in this particular example is more the Zen part of this. So Zen has been using device trees for a long time, both for Zen itself and for the guests. And it has been really hard to do that manipulation by hand. It has been done manually. Typically, you get the Linux device tree, and then you have to, by hand, cut off some things and say that these things are passed through to Linux, these are not, and so on. And that becomes very complicated, especially when you have shared clocks and things like that. And so what we're going to demonstrate is how Lopper can take care of that and rewrite the trees for you automatically. The embedded hypervisors like Zen, the use case there is very similar to AMP, and it's more about isolating different areas from each other. And that's why we have made sure that device trees look the same and act the same for both hypervisor guest as regular domains that you might run on a separate CPU, separate cluster. And here's the second demo, Bruce.
We have a second quick demonstration that shows how the same framework can do a device tree extraction for Zen. So Zen has a concept that you can pass through a device to a guest, and that is done through a device tree snippet or a pass-through device tree, if you will. And that is some, you can either generate those by hand, or in our case, we've written some commands to remove the error-prone part of it to actually locate a device, pull the device along with nodes that will be needed for its proper operation, and pull them into a extracted device tree such that we can pass it through to DOM0, or sorry, DOM-U, and we'll get the device, and DOM0 will allow it to work. So it's actually a little bit simpler in terms of the command line. In order to do this, we are feeding it a host device tree, which could be a system device tree or a normal device tree. And we are writing out a secondary, a modified device tree, if you will. We're passing it through an extraction assist, which knows how to find a device, knows if clocks are required, dependencies. It will chase them down a device tree and will create a new pass-through device tree that is generic. And then we do a secondary call to something called extract Zen, which does final tweaks on the device tree in order to make sure it's in the format that Zen is looking for, because the Zen pass-through device tree predates system device tree and some of the other things, so we need to make it work for its format. There's some other miscellaneous command line options to ignore some nodes, some properties, and to always add some, but that's just us instructing, adding sort of the logic around the device to make sure that we get the right kind of output. So when we run that, you can see that Zen, we found the target serial device in this example. We dropped some mask properties, and then we created something called serial at ff0110.dts. That is the pass-through device tree. So if we have a quick look at that, you can see that it is in fact a device tree, standard format. It has a pass-through node, which Zen requires. It has some compatibility strings, which Zen also requires. And there is the serial device that has been brought into it, and its dependencies of the Zinc MP firmware and the clocks have also been pulled in. We've also added a few different options and properties that Zen looks for, which is the Zen paths, this force assign without IMMU, and the Zen red. So these are things that it requires. And one other thing that we do is there is a virtual interrupt controller provided by Zen. So we tweak the interrupt parent value to be this virtual interrupt controller. So these are all things that those assists are doing. After the device has been located, as dependency has been pulled, it's doing modifications to make sure they're correct. And the one other thing that was the sort of the coordinating step in that run is that if we grep for Zen pass-through in the main system device tree that we wrote back out, you can see that there is now one Zen pass-through property in the base device tree that you would feed to Linux or DOM0, if you will, and that is to indicate to Zen that a device is being passed through and that it should not manipulate it. So that's the coordination value between different steps. I'll do one other quick run, which is to extract, in this case, to show that we can extract an Ethernet device. Everything else is the same. It's a different target device, but otherwise the parameters to LOPR are the same. The only difference we have here is that we're actually reading in the system device tree that was just written, and we're writing out a final one. And that's so we can get multiple values changed within that. So when we run this command, it should eventually run. There we go. So you see that we found the Ethernet device. We did the same thing, interrupt parents. We modified things, and we now have we wrote out something called Zen pass-through ETH DTS in this file. And again, it's very similar. It has different properties, different firmware nodes, different clocks potentially, but it has the same set of Zen properties. It has the same virtual interrupt controller. And because we fed the previous output device tree as the input device tree, it was now updated twice to let us know that there's two devices that are being passed through. So if we look for Zen pass-through now in the final DTS file, you can see that we have not one, but we have two Zen pass-through ones, one for the Ethernet and one for the clock. So we have coordinated with DOM0, and we've produced two pass-through device trees, which would then be compiled into a final image, and you would boot and you'd have a coordinated system. This used to be by hand and it used to be error prone, and we've successfully managed to automate that extraction and generation of the different components. And that is it for me, for my part of the demo, and we will continue with the webinar.
All right, let's talk about what's next for each of these technologies. In remote proc and rpmsg, which Tanmay showed you today for the Zinc MP is not quite upstream. He's been working very hard to get that upstream. And that's going to land in the next couple of kernel releases. And then the rpmsg entitlement will be following that relatively quickly. Arnaud has work on the patches on the mailing list to enable multiple Virtio devices and to declare those Virtio devices in Devicetree. And another feature that's coming along is rpmsg flow control. Qualcomm has published patches that enable this for G-Link, and Arnaud has followed that up with some work to do it for the Virtio rpmsg. But we're also looking at maybe taking this opportunity to make a generic control channel and to provide other services on that control channel. ST has a interesting facility where the secure side of the Cortex-A will authenticate the firmware before it has a chance to run on the remote processor. So this is an interesting use case and has applicability in a number of different scenarios. On the Virtio side, what Dan showed you today is in experimental branches of the library in Zephyr. So Dan wants to get that into the main branch of the libraries and whatever supporting code we need in Zephyr into mainline Zephyr. I want to be able to build the Linux side components of that in Yocto and OE and include that in the CI. And then we also want to port it to other platforms to show that it's something that you can use on multiple platforms. Future work, it'd be very interesting to put Virtio backends on the remote processor. This is kind of the flip side of what Dan showed you today. And then some of these Virtio protocols are interesting enough that perhaps we should look at adding support directly into the kernel to run these in an AMP fashion. I think VSOC would be the most interesting one to look at first. For system device tree, Bruce has already done Yocto integration, but to get that working a little bit more and make it applicable to other people's build flows. They showed bare metal and FreeRTOS today, but integration with Zephyr is an interesting use case, especially because Zephyr has its own Devicetree based build flow. So there's some interesting problems to do there, but I think it could be a very powerful combination. And then the Zen partitioning that they showed today, make that productized, make it usable by multiple people. And then Bruce is also talking about adding functionality to Lopper to do comparison and verification of the Devicetree. From a CI point of view, I've already talked about wanting to be able to build and regression test the PRs as they come into the library and the patch series as they come in onto the remote proc. To do that, we're going to need to increase the test coverage, and the release automation also requires that test automation, test coverage enhancement. We have a good start on the documentation. This is relatively new. Tammy Lino from Siemens has been doing great work for the whole project, doing code quality on the libraries. A number of enhancements have come in, fixing bugs that have been there for quite a while. So great contributions overall, but in the past couple of months, she's collected documentation from various bits and bobs around the project and collected them into a single repository. We can drive the whole documentation process. So this is a new repository, OpenAMP docs, and we can build that and publish it to read the docs, which is a link that's there, and then the source to the repo is there as well. So going forward, we want to clean this up and synchronize it to the releases. So in the spring release, we hope to have a synchronized release between the documentation and the libraries, and whatever the kernel requirements are at that point. We'd like to add to the document a wire protocol specification that's independent of the kernel or the libraries, any implementation specific, so describing what's the ground truth of the wire protocol. And this is things that aren't documented already for Virtio upstream at Oasis. We're talking about enhancements to the resource table. I talked about that control channel enhancement. A good way to drive those discussion of those enhancements is to write documentation PRs that change the specification to show how that specification would change with these enhancements. So coming out of today, what we'd like you to understand and remember is that remote proc and RP message is usable in Upstream today. If you're an end user, hopefully you can start using this. If you're a silicon provider and your platform isn't already working upstream, now would be a great time to engage with us. For hypervisorless Virtio, we would like you to understand that Virtio is a very powerful standard, and that this work allows you to use that powerful standard on AMP systems. For system Devicetree, the main concept is a single source file can let you configure all the different runtime environments, Linux, RTOS, Zen, bare metal, and others. All right, so now we want to show you how you can try some of these things that we showed you today on your own. All right, hopefully I'm live. All the panelists and speakers that you've heard today are here live. So we're going to talk about how you can try things on your own, and then we're going to do Q&A. All the questions that you've asked during the session, we'll cover those, and then any questions that come up live, we'll tackle those as well. If we could go to the next slide, please. All right, so the demos that Tanmay showed you today and that Dan showed you today are available in a Docker image. And there's more demos in there. There's a There's a Upstream Xilinx demo in there that uses a Hello World Zephyr application. The split mode is in there as well. But a number of those, but then also what the demo that Bruce showed you is also in there. It's pre-set up, and it has some scripts that'll walk you through it and point you to the right README to follow along. So if you were having trouble reading the slides today, you should be able to do those demos yourself and look at exactly what's happening. If for some reason you can't run Docker, here are some links to the READMEs for the individual parts of the things that we showed today. The system DT demo README there is the README that you would be following along in the Docker container for the system DT. All right. So we're here live to answer your questions. If you're trying this on your own later, we have a community Discord that we've set up. The link here will let you join that. After you join, you can join the OpenAMP community channel if that didn't happen automatically. There is a 10-minute wait time from the time you join until you can answer your first question. Hopefully that's not too problematic. So any of the demos you have trouble running, please ask us questions on that Discord. If you have other questions, more involved or something like that, we would encourage you to join the mailing list. And you can find all the mailing lists at the homepage for the project, which is openampproject.org. Okay. Hopefully that's clear. Let's go to the next slide. So as I said, all the panelists that you've heard today are here. We also have Tammy and Matthew joining us. Tammy, again, I mentioned she did work on the documentation, but she's also done a lot of good work in the QA of the libraries, and Matthew is the maintainer that we rely on a lot for the kernel work. All right, let's start with the questions that we got. So Nick asks, our company Linux RP message outside of our OpenAMP is currently pretty limited. Each RP message packet must be exactly 512 bytes, no options like interrupt only, 0 copy, shared memory, etc. Does OpenAMP add any additional flexibility to IPC? Arno, are you going to take that one?
Yes, I can. So that's right. Today, the Linux rpmsg framework imposes, for the Virtio implementation at least, that the buffer has a size of 512 bytes. So this is the today limitations. I think that Matthew will be happy if someone proposes something to make this more flexible. On the opponent side, we can select the size of the buffers in reception and transmission. We can have 2 different sizes, but to be compatible with the Linux and to communicate with the Linux, we also need by default to be at the same size of the buffer. Concerning the possibility to have some interrupt, it's more a service on top of rpmsg that could propose interrupt. If you want equivalent of the Virtio IO that allow you to have some interrupt from a virtual OS or something like that, you need, in fact, for rpmsg to implement it as a service. But one issue and one limitation is that the rpmsg allow to mix several services. So if you want something under interruption, for rpmsg, you have to put all the rpmsg framework under interruption. So it's better to use a mailbox instead for that, if it's possible, or use the Virtio IO implementation. The last point is zero copy. The Linux rpmsg remote proc don't allow the zero copy. The OpenAMP library allow it.
So OpenAMP library to OpenAMP library, you have a lot more options.
So one solution, if you don't want to have this kind of limitation, is to implement the OpenAMP library in the user space and communicate directly using Open Library between the Linux user space and the remote processor.
Okay, thanks. So Hiago asks, which device tree modifications are needed to give the remote processor access to the master file system as presented in demo 2? And Tanmay, you're going to take that question.
Sure, Bill. Thanks. So short answer is no, we don't need any device tree modifications, assuming vendor-specific remote proc nodes are available in the device tree. So essentially, I think this needs more description. So on the remote processor side, OpenAMP libraries rpmsg retarget is being used to redirect sysfs calls to host processor's file system. I'm posting a link to rpmsg retarget implementation that is available in OpenAMP in answers. So that is how the whole thing is basically implemented in OpenAMP library, user space library only, and we don't need any changes in device tree.
Okay. I think the rest of the questions were about the fuzziness of the video, which hopefully you were able to make work on YouTube. Oh, we have another one here. Will OpenAMP provide fine-grained control over the whole system? For example, to be able to reboot individual subsystems. So I'll tackle that one. So whether it's part of OpenAMP or not might be a little bit debatable, but certainly in this scope of things that we're talking about, yeah, there's we've certainly talked about like a safe island being able to reboot, you know, the other parts of the system. We talked about in the future work, I didn't really talk about it today, but we want to have robustness guarantees so that if one component fails, it can be rebooted and the system can resynchronize and communication can restart. That applies to rpmsg, but other facilities as well. Anybody else have an answer to that question that you would like to provide?
Yeah, we also have some support in the system device trees so that you can actually create a domain or a subsystem of things that belong together. At the AMD Xilinx, we use that so that the firmware knows what parts belong together so that you can reboot part of the system and not the rest of it. So from a configuration point of view, there are certainly things you can do there. But typically the actual starting up something that's in the firmware, and it's probably hard to generalize because all our firmwares look very different.
Good, thanks. Detlef is asking, is there an example for the user space OpenAMP usage in Linux? Depending on what you mean by user space usage, there's several examples. So Xilinx implement, so they can use the rpmsg that's in the kernel, but they also have the mode where you compile a library and run it in user space. And so they rely on remote proc in the kernel, but use rpmsg from user space. The tricky part there is you need to figure out how you're going to do the kick and notify. And Xilinx uses UIO for that, or at least in one instance they do. Of course, Arnaud showed a number of examples about just sort of using rpmsg, not implementing rpmsg from user space. So I'm not sure which aspect of that the question was aimed at.
So maybe to add to that is that the libmetal library, that's sort of the porting layer, if you will, for some of these things, that is ported to user space, at least on the Xilinx platform. That's what Bill was just talking about. So it makes Linux kind of look the same as user space Linux look the same as when you run it on a separate core. So it's the same code with a different underlying porting library there.
Yeah, and so in the documentation that we pointed at, there's one example in there that's Linux to Linux remote proxy example. So the proxy example that Tanmay showed you today, which is kind of a semi-hosting, using that one from one process in Linux user space to another process in Linux user space. That's kind of an artificial use case, but it's good for testing the code and proving that this works. So that might be something you might want to look at. Okay. Yago I have some modules that use NXP IMX7 and IMX8. Would I be able to use the OpenAMP on them? Yeah, the Cortex M4 coprocessors. So NXP in general has done a good job about getting their remote proc support into Upstream kernel. So that should be good news. The Zephyr M4s, the M4s I think are well supported in Zephyr. So I think it should be fairly easy to get that working. NXP often uses an alternative implementation of rpmsg called rpmsg Lite, which was a little smaller, especially before we did the lightweight skinning down of the library that I talked about earlier. So you may find examples for that also. But I think if it doesn't work out of the box today, I think it'd be pretty simple to get that working.
I think there are already some contribution in Zephyr on an example that allow to communicate with Linux.
Okay.
And there are some contribution to be able to use it for NXP EMX platform also. I don't think that it's merged today, but I saw some contribution.
Okay. All right. Any ideas on attestation being built into OpenAMP? I think that's kind of related to the secure world verifying the remote proc firmware. Do you want to talk about what you're doing there, Arnaud?
Yes, it's more about authentifying a remote proc firmware before starting it, in fact. So what we are doing in ST for that is that we delegate the load on the start of the firmware to the secure part instead of loading the firmware by the remote proc framework in Linux. So that means that for that we use Opti, and the Opti gets the image of the firmware in RAM, verifies the signature thanks to a private key, or public key, sorry, and then load it in the destination RAM of the coprocessor, authentify it by section, and when everything is okay, it starts it. and it can also isolate the memory to be sure that Linux have no more access to the remote proc firmware code.
Yeah, and so this is more security than attestation, but some people are looking at IMA framework and the associated technology, I don't remember what it is, to verify everything that's in lib firmware before using it. You know, so that mostly applies to a read-only root file system, but with FS Verity, I think the feature is called, that may be able to be something that could be applied even on a read-write file system. For remote attestation, you know, the firmware could be measured into PCR on TPM as if it was an early boot component or something like that. So lots of different aspects. Hopefully there's something that goes to the core of your question in that. Okay, that Lev. More freedom for zero copy, for OpenAMP. Okay, good. We kind of answered your question. Great. So will rpmsg Lite from NXP be depreciated? That's really up to NXP. I don't necessarily envision that happening. I think our goal is to make diminish any reason for you know, if there's a deficiency in the OpenAMP library, that we address that so that that deficiency doesn't exist. As we add more features of like the VirtIO devices and stuff like that, those are definitely going into the OpenAMP library, and I think it would probably be counterproductive to address those new features into rpmsg Lite. All right. So keep me honest, people. I think, have we covered everything that we had? We have 10 minutes remaining.
So I think we covered everything in the Q&A tab, but does your company have to be an OpenAMP group sponsor or like a group member in order to contribute to the code base?
So the answer is no. Obviously, you can contribute to the code base. You can attend our meetings. All of our meetings are advertised on the mailing lists. Participation is open. So answer is no, but we would love to have you. Fees to join are very modest and help support the project. You want to pick another one, Natalie?
Sure. I guess maybe this is one for Arnaud. What are the release timeframes?
So concerning the OpenAMP library itself, we release twice per year, in April and October. And we freeze the code, or I would say at the middle of April and October, and output the release at the end of the month.
So
Thanks.
I have a question for Bruce. He didn't tell me not to ask it, so I'm going to ask it. Have you thought through about how Lopper would work with Zephyr?
We didn't have to think through it. We have periodic meetings and sync ups with various
Right.
people in that community, and So yeah, it's something we're working through how exactly to use it, whether it's the system device tree specification and some different set of Python tooling that we can share, or Lopper itself, or some sort of pass-through. So it is something that is being explored with, I guess no one answer right now.
Okay. Yeah, I mean, I think we all saw Marty in the attendee list, so hopefully will progress well.
Hey, Bill, I have a question.
Yeah.
Since somebody brought up rpmsg Lite, I was wondering if we wanted to discuss the interoperability between rpmsg and rpmsg Lite. Like, does rpmsg Lite work with OpenAMP full distribution?
That's a good question. I'm not sure I don't think we've ever tested it. I don't really know too much about rpmsg Lite. Does it conform? One of the things I said we did want to do in the documentation was create the wire protocol definition of rpmsg. And rpmsg is a back compatible technology. So even as we add features to rpmsg, the base level should continue to operate. So yeah, that is a good question. There are other people that have implementations of rpmsg. And so certainly the kernel is being tested with multiple implementations of rpmsg. But two sort of RTOS bare metal implementations, I don't know if that's been tested. It's a good question.
What we can add is that for OpenAMP, we try to keep compatibility at every time between the Linux and the OpenAMP library. I don't know about rpmsg Lite. I guess it should work, but perhaps without some feature, or the feature come later. I don't know. But one of the objectives of the OpenAMP is to keep compatibility with the Linux kernel in the OpenAMP. We have some extra feature in OpenAMP that are not compatible with the Linux, but we can disable them. For instance, as we mentioned, to be able to customize the size of the buffers.
So here's a question. How does OpenAMP relate to embedded hypervisors such as Zen? So I'm going to say Thomas should answer that.
Sure, I can talk about it. So we saw in the demo, obviously, how you can use system device trees for both Zen and for AMP. In general, what we're trying to do is to make embedded hypervisors look the same and as similar as possible as AMP. The mental model I have is that you're using the hypervisors really just to isolate the different cores and the different memory systems, right? So it looks very similar to AMP. So we're going forward, we're looking at other things to harmonize the Virtio from a hypervisor to AMP to make sure that it all works together. So definitely going to do more with hypervisors going forward. And right now, Zen has been the focus for what we're doing, but there are other, and then there are proprietary hypervisors, of course, from people like Wind River and Siemens and so on. But also interested in if other people want to add things like for Jailhouse and stuff like that, that would be super interesting to add to the project.
Great. Have a time for at least one more question. We have a question. So I'm interested in system device tree. How do I participate? So Bruce, Natalie, who wants to answer that one?
So I guess in terms of joining the community calls, if you join the mailing list, we'll send any call invitations there. The calls are every few months. Bruce, do you want to take?
I was going to say both of them are sort of on demand. We have that call every once in a while, and we also talk a little bit about it during the OpenAMP call. So you're welcome to join there. You hear a little bit about system Devicetree on those calls. But yeah, Lopper is part of the Devicetree .org GitHub, if you will. It's a sub project. So there is a Git repository and a mailing list that you can find all the resources by if you just search up Lopper GitHub, you will find the right place for the source, and all of the forums and mailing lists and everything are reachable through that GitHub project.
All right. Matthew, if you don't mind, I'll ask you for a 1-minute summary of what you think the status of remote proc and RP messages in the kernel. Are you pleased with the community engagement? What's going on?
Pleased with the community engagements to some extent. I like the patches that are coming in. The big problem is reviewing patches as usual. So having people that are looking at patches, providing comments for patches. So that allows other people to chime in and give their opinion, which helps me a lot because I can see what people need and where people are going with their implementation. And without comments like that, it's really hard for me to judge, what specific features should be when they are difficult. Sometimes I'll ask for people to review certain patch sets, and I think for the most part that works well. I'm really appreciative of that because, again, it gives another view of the perspective that people might have in their own environment that are completely opaque to me. So this is interesting, but again, from participation and reviewing patches, this is probably the best, the biggest problem that I have. Sometimes we have a lot of patches that are accumulating. And it's not because I don't want to look at people's work, it's because I simply do not have the bandwidth. So having more people looking at code helps me really concentrate on tedious problems that require my involvement, and also helps having a better view of what people are facing in their environments. So for the most part, this is what I think. Otherwise, I think people are working well. I think there's there's no real problem with regards to patch submission or anything like that. For the most part, it just follows the kernel convention, and I'm quite happy with that part.
Good. So I pulled those statistics. I hope you saw them earlier in the presentation about how much we've accelerated in our patch acceptance. I want to personally thank you, Matthew. I think your involvement here has been great, and that success is really tied to your involvement. So thank you very much.
Yeah, happy to do it. It's a fun subsystem. The people are interesting. The hardware is interesting. Keep sending patches and keep reviewing patches.
Okay, great, thank you. All right, I think unless anybody has any final thoughts, I think we'll leave you there. Please try out our demos. We worked pretty hard on them. So, and hopefully we'll talk to some of you on the mailing list, the Discord, and Linaro Connect for the spring has been announced. So hopefully we'll see you there. Thank you, everybody.
Thank you. Thanks.